Find an equation of the tangent line to the curve y equals 1 plus 2x squared at the point 1, 9. So if we're looking for the equation of the tangent line, that means that we're looking for the derivative. And if we're looking for the equation, that means we're going to use our y minus y1 equals m times x minus x1. And we're going to look at the derivative to give us our slope. So that m value will come from our derivative. So first things first, we need to be able to take the derivative here. So we have y equals 1 plus 2x. It's the quantity squared. So that means 1 plus 2x times 1 plus 2x. So we need to FOIL this through. We need to clean this up so that we can take the derivative. So that would be y equals, do your FOIL. So 1 times 1 is 1. 1 times 2x is plus 2x. 2x times 1 is plus 2x. And 2x times 2x is plus 4x squared. Now we can take our derivative. Well, let's simplify it one step farther first. So 1 plus 4x plus 4x squared. There we go. Now let's do our derivative. The derivative of 1 is a constant. So the derivative of 1 is 0. The derivative of 4x, x is technically to the first power. Bring down your power. So 4 times 1 is still 4. And then x to the 1 minus 1 would be x to the 0. So that's just 4. Plus 4 times 2 is 8. X to the 2 minus 1 is 1. So 8x. So we've got our derivative. Now we have a point. So y prime equals 4 plus 8x. Look, we have an x, we have a y. So if we put in our x value, so 4 plus 8 times 1, that's going to give us the derivative at x equals 1, which will be our slope at x equals 1. So if we do that, we have 4 plus 8, which gives us 12. So that means our slope at 1 is 12. So now we can put it into our equation that we have over here. We have 1x and we have 1y from our 1 point. So y minus y1 equals m times x minus x1. If we solve it down, we have y minus 9 equals 12x minus 12. Add 9 to both sides, and we get 12x minus 3. So this will be the equation of our line, of our tangent line, at the point 1, 9. If you had a different point, you would just use the same approach for the derivative, and then use the different x in the middle step right here to find the slope at that point. Let's look at this one. If f of x equals 3x to the 5th minus 20x to the 3rd plus 50x, find f prime of x. And then we're comparing the graphs. So let's first start with finding f prime of x. So that is our derivative. So we have 3x to the 5th. So bring down your power. So 3 times 5 is 15. And then we have x to the 5 minus 1 is 4. Minus, we had 20x to the 3. So bring down your power. 3 times 20 is 60. X, and then 3 minus 1 is 2. We had 50x. So bring down your power. So 50 times 1 would be 50. And then x to the 1 minus 1 will give us x to the 0. So just plus 50. So here's our derivative. I graphed the two functions for you. Here's the derivative graph. Here's the original graph. So if we look at these, what can we notice? Well, let's think back to our graph behavior when we are looking at graphing the derivative. So for our original function, when our original function is increasing, our graph is above, our derivative graph is above the x-axis. So that looks about right. Our original function right here is increasing. See, it's going up. And our derivative is above the x-axis. And then look right here. Right here is where it stops increasing and it starts decreasing. So if it starts to decrease, that means that our derivative is going to dip below. And look right here, it dips below. It's still decreasing until we get to right here. And then it starts to increase again, which is why we have it crossing the axis again. And then it looks like it increases all the way, oops, wrong one. It increases all the way up to increasing here. So it stops increasing right here. Notice our graph is above the axis this whole way. And so this whole way where it's increasing, it's above the axis. And then right here where it stops increasing and it starts decreasing, the derivative dips below. And then when it starts increasing again, there we go, the derivative goes back above. There we go. So it's a lot to compare, but we can look at our increasing and our decreasing regions, and we can compare them between the original function and the derivative function. Let's practice a couple more derivatives. So for this one, we're trying to find the first and second derivative. So remember from before, we said that if we look at the power here, this will tell us how many times we can take the derivative until we would start getting it down to the constant and then 0. So here we could take the derivative 4 times. We're only asked for up to the second derivative, but we could keep going if we really wanted to. So if we're looking for our derivative, start with the first derivative. So f prime of x. We have x to the 4th, so bring down your power. That will give us 4x to the 4 minus 1 is 3. We have 3x to the 3rd, so bring down your power. 3 times 3 is 9. X, subtract 1. 3 minus 1 is 2. We have plus 16x. So bring down your power. It would just be 1. 16 times 1 is 16. And it would be x to the 0, so that goes away. So then for our second derivative, so f double prime of x. Second derivative, f double prime. 4 times 2 gives us 8. Whoops. Backtrack. It's 4 times 3. Let's try that again. Bring down your power. 4 times 3 is 12. 3 minus 1 is 2. Bring down your power. 9 times 2 is 18. 2 minus 1 is 1. The derivative of a constant is 0. So the derivative of 16 is just 0. Now it only asks us for up to the second derivative, but if we wanted to keep going, we could. Let me show you the notation for the third derivative. There you go. Sometimes you might also see it like this, triple prime. But after triple prime, it all resorts to just the little number in parentheses. So these, either way, same thing. But if we take our derivative, 12 times 2 is 24. There we go, try that again. 2 minus 1 is 1. 18x, the derivative is just 18. These are extra, I just wanted to show it to you. And then if we take the derivative again, the derivative of 24x is just 24, and the derivative of 18 is 0. Remember we said originally you could take the derivative 4 times, and then after that you would be at a constant, and the next derivative would be 0. Well, there you go. Let's look at number 13. I prefer to rewrite these. I don't like to look at the square root when I'm trying to figure out the derivative because I find that harder to hold in my head with the numbers. So I change them into fractions and then I consider the square root. To me, that's just easier. Then you can bring down your power. So I see that 1/2. And then if we are subtracting 1, so if the denominator is 2 and we're subtracting 1, it would look like 2 over 2. So 1/2 minus 2 over 2 is negative 1/2. And then if we bring down our power, so 1/3, and then we subtract 1, well, subtracting 1 when the denominator is 3 will look like subtracting 3 over 3. 1 minus 3 is negative 2 over 3. Our second derivative, bring down your power. So now be careful. If I have 1/2 and I'm multiplying it by negative 1/2, that's going to give me negative 1/4. 1 times negative 1 is negative 1. 2 times 2 is 4. So that'll be negative 1/4. And then I'm already at negative 1/2 and I need to subtract 1. Well, subtracting 1 really looks like 2 over 2. So negative 1/2 minus 2 halves. So negative 1 minus 2, that's going to give us negative 3 over 2. And then we still have our same work for the 1/3. So we have 1/3 already times negative 2/3. 1 times negative 2 is negative 2. 3 times 3 is 9. So this would look like minus 2 over 9. And then same thing, we have our we have negative 2/3, and we need to subtract 1. So if it's thirds, 1 will look like 3/3. Negative 2 minus 3 is negative 5. And then our denominator stays the same as 3. So this would be our second derivative. Yes, if you wanted to, you could drop the negative exponents and do it in the denominator and make them positive. Either way is fine.